Welcome all. Today we are going to study division, division of fixed point binary numbers. So let us see how two numbers which are in signed magnitude representation can be divided. Let us take an example. Let us say we have to divide 448 by 17 and both are positive. So the divisor is plus 17 and the dividend is plus 448. So if we represent these numbers in signed magnitude binary form, plus 17 will be, this will be plus 0 represents the plus and the remaining 5 bit represents 17, and here this is plus and these remaining 10 bits represent 448. We are supposing here that this is represented by a 5 bit in a 5-bit register and this in a 10-bit register with separate flip-flops for sign bits. This division of signed magnitude binary numbers is very similar to what we do using a pen on a paper, the division that we do of decimal numbers. So if we do it on a paper, we can do it like decimal numbers. So we can keep a divisor here, a dividend here, and start the division process. As in the binary numbers, since this is 5, we check the size of this thing and this first 5 digits here. So let us suppose that this divisor is in B and this dividend is here A. So let us check the first 5 bits of A. So these are 0, 1, 1, 1, 0, and the divisor is 10001. So obviously we cannot subtract this thing, this divisor from this. So as in decimal, we bring an extra 0 from here, an extra digit from here, then only we can proceed. So this 5 bits obviously cannot be, we cannot do a subtraction of this and this because this is smaller than the divisor, the first 5 bits of dividend. So we say that since the 5 bits of A are less than B, so we need to make this 6 bits. So if I have to make it 6 bits, so I will make an extra digit from here, so it becomes 6 bits. Fine. Now these 6 bits are greater than this divisor. This is greater than the divisor. So then I start the division. I say this into 1, in the quotient I put 1, right? So this into 1 will be 10001, which I write here. This 10001 would come here, starting from here. So I need to do a right shift because I have to bring it beneath these bits. So that is why I do a right shift in B, that is the divisor, and do a subtraction. And at the same time here I mark 1. So let us do a subtraction. This minus this, it will come out to be 0, 1, 0, 1. Fine. Then as in decimal division, I bring a next number from here. So next is 0, I bring a 0 here. Now again, these 7 bits of remainder are greater than this B, no issues. So this into 1, I put a 1 here, comes out to be 10001. We do a subtraction here, get this thing 00101, and then get another digit from here, it becomes this. Now this remainder is again less than b. So whenever this happens in division, we bring an extra digit from here. So since we bring an extra digit from here, we need to make an entry here of 0. Same procedure which we do in normal decimal division also. So to bring an extra digit from here up to here, we put a 0 in the quotient. So after doing this again, we see that now the remainder is greater than b. So I can say this, I will put 1 here, this into 1 comes out to be 10001. Do a subtraction, that comes out to be 00011, and bring this 0 up to here. Fine. Now again the remainder is less than b. So since this is less than b, I need to put a 0 here and bring the next digit down. But after that we see that there is no further digits after this 0 has been brought down. So since there are no further digits, we stop the procedure as in decimal division. So we say the answer is, this is the quotient and this is the final remainder. So to cross check, we can see that when we divide 448 by 17, the quotient comes out to be 26. It should come 26 and remainder should be 6. So we can check that this is 6, this is 6, and this quotient we can convert to decimal, it comes out to be 26. So now what will be the sign of remainder and quotient? Obviously the remainder will always be positive and the quotient will have a sign depending on the signs of dividend and divisor. So we can, if both are positive, the quotient will be positive. If one is negative, the quotient will be negative. And when we do a hardware implementation of this, we know that for performing this thing, we use an XOR gate. So we will do an XOR. If both are same, both are positive or both are negative, with the sign bit of the quotient will be XOR of both. So if both are positive or both are negative, the quotient will be positive. And if the divisor is positive, the dividend is negative, or vice versa, the quotient will be negative. So this is how we do it on a paper. Now coming to an algorithm which can be used here. For division, we use this algorithm which is depicted in terms of a flow chart. So this is the flow chart, that if we follow this flow chart, we will perform the division of two binary numbers that are in signed magnitude representation. So what does this flow chart say? It says that put the dividend in AQ. So we need to use two registers in a serial fashion. So since the dividend is 10 bits, we put 5 bits in A register and 5 bits in Q register. So the dividend is in EAQ and the divisor is only 5 bits. So it is in a single register. Let us call that B. Then we, to know the sign bit of the quotient, we do an XOR of the bits, sign bits of A and B. Then we start this process by putting the counter to n minus 1, because we don't use this sign bit here inside. So this minus 1 is of that sign bit. We remove that 6 bit, that is a sign bit, and we will start the counter from 5 for this example. So the first thing I need to do is that I need to check whether A is less than B or not. Before performing division, I need to know whether A is less than B or not. What is A? A is the first 5 digits of the dividend. So the first 5 digits of the dividend should be less than the divisor. Why? If it is greater than the divisor, then the answer, the quotient will be of 6 bits. Naturally, it will be of 6 bits. If the first 5 bits of the dividend are greater than or equal to the divisor, naturally the answer will be of 6 bits. But the quotient is stored in a register which is only 5 bits. So such a case cannot be taken into consideration. So if the A is greater than or equal to B, such case we cannot take into consideration. We cannot, our that computer will be incapable of doing that. So for checking whether A is less than B or not, we have to do this procedure here, this procedure. So a simple way to check whether A is less than B or not, first we do an A minus B, which is same as A plus B complement plus 1, and then we check the carry bit. If this extra bit, carry bit, is 0, then no issues, A is less than B. If it is 1, then we cannot do this division. We just convert back the number and write the flip-flop as this flip-flop DVF has 1, which means that there is a divide overflow. This is a divide overflow flip-flop. So divide overflow end. And if this is 0, that means A is less than B, we can perform this division. And but before performing the division, we need to convert A back to its original form. So to convert back, we need to do this A plus B and put the overflow as 0. So all this is done to check things. So since we have checked it is okay, then we need to convert back. We have done A minus B, we need to do an A plus B. So now we get the number back. Now this right portion is the actual division thing. This is the actual division which is happening here. This left portion was here to check whether we can do this division or not. And this thing is for calculating the sign bit. So when we go here, we do a division, which is a simple one. First we do a left shift, then we follow these lines, and we will get the answer after certain iterations. So we need to do an A minus B, then again check whether A is less than or B or not, and do the things like that. So we know that if A is less than B in division, in between division, we need to bring an extra bit from above. Then we need to put a 0. So let us understand fully this flow chart using an example. So here on the left hand side, you can see an example, this one. So the same example is that the divisor is this number and the dividend is this. So this is the same example. So this is the dividend. So the flow chart says put the dividend in AQ and the divisor in B. So the dividend I have put in A and Q here. So dividend is 0, 1, 1, 1, 0, 0, 0, 0, 0, 0. And then put the SC as 5. We start. The first thing we do will be here. So we do a left shift of EAQ. So this left shift of EAQ means this and this will be shifted left. So this will come here, this 0 triple 1 and followed by 6 zeros will come here, 0 triple 1 followed by 6 zeros, and then there will be an empty place here that will be filled with 0 because this is a logical shift. Fine. Then we do an A minus B. So when we do an A minus B. So A minus B is same as adding 2's complement of B. So I add this 2's complement of B to A here. We get this thing. If we do an addition, we get this thing with a carry which comes here. So then I have to check E. If E here is 1, obviously this is 1, then I have to do this thing here. The flowchart says that E is 1, then put Qn equal to 1 and again iterate. If E is 0, then put Qn as such, but do this addition and iterate. So since E is 1, I put Qn equal to 1. Qn means the least significant bit of Q. So this 0 is to be converted to 1, Qn, fine, and restart the iteration. So this SC will be 4 now. Now again, do the same steps again. Do a left shift of EAQ here, done. Then subtract B or add B's 2's complement of B, done. Check E. It is again 1, again perform, again put Qn equal to 1. Okay, and do a decrement in this SC. Again, do the shift EAQ. I have done the shifting. Then add 2's complement of B added. Now E comes out to be 0. So the flowchart says that when E is 0, add B and move further. Don't do anything to Qn. Leave Qn as 0. Add B. After adding B, I will get this thing. Fine. Then again restart the iterations. So again do a shift, again subtract, then check E. E is 1. Put Qn equal to 1. Decrement. Again shift, again subtract, again check E. E is 0. Leave Qn as such and add B. You will get this thing. And when the counter comes near to 0, you are done. In A, whatever is in A, this is the remainder. Whatever is in Q, this is the quotient. So automatically in A, finally, it will be the remainder, and in Q, it will be the quotient. So what needs to be remembered here, that we start, the first thing we need to do a shift left operation, then a subtraction, which is same as 2's complement addition. So the first is shift left, second is subtraction, third is checking E. If E is 1, put Qn equal to 1, done. This needs to be repeated. And if Qn comes out to be 0, this E comes out to be 0, then we have to redo this thing. This subtraction has to be redone. So to redo this thing, we need to add b. We just did an a minus b. Now again we need to do a plus b to get back the previous remainder. That is why this thing is called restore remainder. So this remainder is restored back previous remainder. So so we need to follow these 1, 2, 3, and 4 steps. They need to be repeated and repeated. The only difference will be in this thing. If e is 1, then do this, and if e is 0, then do this. If e is 1, you have to put qn equal to 1, and if e is 0, don't change qn but add b. And if we repeat these 4 steps continuously, we will automatically get the answer, and we can check that this is the answer. This is 6, and this answer will be, which we already saw, 26. So this is the same example. So answer is same. This 11010 is quotient, and 00110 is remainder. So 11010 is quotient, 00110 is remainder. Thank you.